Hello, everybody.
Hi, Professor.
Okay, I'm going to wait a few moments. I guess we have some people still coming in. And we got record. Okay, so while we're waiting for a few stragglers here, the plan for tonight is we still had a little bit of conversation they have about section properties from the lecture before the midterm. So I want to finish that out first, kind of complete that whole thought about geometric section properties. I don't think that's going to take more than 10, 15 minutes or so. Then what I would like to do is go over the midterm, and I'm actually going to put my solution to the midterm up, and we're going to walk through it kind of step by step. And then with the time that we have left after that, we are going to introduce a new topic for tonight, which is torsion design, which is chapter 5. So that is the plan. Let me, one other thing I wanted to bring up. Bear with me a second. Okay. Okay. So I have the numbers that I want. All right, so let's start with finishing out this section properties that we started last time. Okay, so the last subject that we didn't have time for last time is principal axis. And basically the idea is if a shape is unsymmetric, then the maximum and minimum moments of inertia will not occur on the X and Y axis. Very inconvenient for us, but that's not where the maximum and minimum will occur. So we're going to use this thing called the product of inertia to find the maximum and minimum moments of inertia. Product of inertia is equal to this. It's labeled as, remember last time we talked about, we have moment of inertia I about the x-axis, moment of inertia I about the y-axis. The product of inertia is about both axes. So it's labeled Ixy and is the integral of the area x times y. If you remember from last time, moment of inertia about the y is x squared. Moment of inertia about the x is y squared. Well, this is going to be x times y. So for a symmetric section, the product of inertia Ixy equal to the integral of the area x times y is equal to 0. If it is symmetrical, then the product of inertia is always equal to 0. For an unsymmetric section, however, it is not equal to 0. It is equal to the moment of inertia or the product of inertia xy about its own axes plus a times dx dy. For the minimum and maximum moments of inertia, the maximum is going to be ix plus iy over 2 plus the square root of the sum of the squares. Ix plus iy over 2 squared plus the product of inertia Ixy squared. The minimum is going to be Ix plus Iy over 2 minus the square root of the sum of the squares. The minimum and maximum moments of inertia are oriented on an axis at theta to the x-axis, where theta is equal to half of the inverse tangent 2 times the product of inertia over Iy minus Ix. So this gives you an angle. This tells you how many degrees from the x-axis that the maximum and minimum moments of inertia are oriented to. Okay, an example maybe?
Professor, sorry, could you go back real quick?
Sure, sure.
Thank you.
No problem. Okay, so let's do an example. Here is an unsymmetric section. And I work in the world of concrete. We do concrete beams that are shaped like this. So this, for me, is a real world example. So that's why this is a fairly large member. The wall is 8 inches thick. The ledge is 12 inches thick. The ledge is 30 inches high, and the wall is 50 inches high on top of that. Because this section is not symmetrical, then it's going to have a maximum and minimum moments of inertia about some axis other than the convenient x and y axis. Okay, so let's put some numbers on this. What we want is the minimum and maximum moment of inertia. Start with finding the area. The area is 8 times 50 for this piece, plus 12 times 30 for the bottom piece. And I just found my first typo. Oh, that's great. This piece is 8 times 50. This piece is 20 times 30. This is slide 279. And I got 1,000. I'm wondering if that's the right number or not. Let's see, 8 times 50 plus 20 times 30. Okay, it is. Okay, sorry everybody. The typo is the 12 right there. That's supposed to be 20. But the number 1,000 inches squared is correct. Okay, so let's find, basically we start with finding where the center of gravity. Oh, why is it 20? Oh, here, let me do this. An example problem's not very good if everybody's confused from the very beginning. This is area 1. This is area 2. Okay, so this is area 1, this is area 2. Area 1 is 8 wide by 50 high. Area 2 is 8 plus 12 is 20. So area 2 is 20 wide by 30 high. It's 8, not 5. Does that make sense to you guys? Oh, there's a lot of chat on that.
Yeah, it's obvious now.
Okay, did that clear it up for everybody?
Yep.
Okay, great. Okay, so what we want is where is the center of gravity of the whole section in the x direction and the y direction. So I've got the area 1, which is 8 times 50, plus 8 over 2 is 8 over 2 is to the center, plus the typo again, 12 times 30, that's 20 times 30, plus 8, and then, oh, that's just totally wrong. Hopefully I got the right answer, even though I got the wrong equation. 7.6 inches, I believe is the right answer, but I got these numbers in here. I messed up. So I got to fix those too. But anyway, you guys know how to find the center of gravity. It's the average of the 1 and the 2 over the total area. And the same typo is going to be pervasive. But in the y direction, I've got 8 times 50 plus 30 and half of 50 gets me to the center. Here, this is 20 times 30 times 30 over 2 gets me to the center, and that center of gravity is 31.0 inches. I've got, in my daily work, my real job, I've got MathCAD templates that are set up that calculate all this stuff automatically. So I'm pretty sure these are the right answers. You just can't get there with the wrong numbers that I had for area 2. Okay, so here is the center of gravity for the whole section, 7.6 inches over, 31 inches up. And I'm going to create this little table. So I'm going to create the part number, the moment of inertia in the x-axis, and the parallel axis theorem, which is the area times the distance squared. So for part 1, I have 8 times 50 cubed over 12 is 83,333. I've got 8 times 50 times 55 minus 31. 55 is 30 plus 25 minus 31 squared, gives me 230,400. Part 2, and again, I got the same mistake, it's just going to carry all the way through. But this was 20 times 30 cubed over 12, 45,000. And 20 times 30 times 15, see, oh yeah, 50, we're still in the vertical direction. So half of 30 is 15 minus 31, 153,600. So my moment of inertia about the x-axis, I add all 4 pieces together, I get 512,333 inches to the 4th. Again, this is a pretty big section. This is 80 inches, which is 6'8" high. It was a pretty tall beam. Okay, in the moment of inertia about the y-axis, I do the same thing. Only now everything's switched because I'm summing about the y-axis, not the x-axis. So for part number 1 about its own center of gravity, 2133, and then 50 times 8 times 4 minus 7.6 squared. 4 is the center, 7.6 is the center of gravity. That's 5184. Part 2, 30 times 12 to the 3rd. I'm going to quit pointing out where all the typos are on this, but 20,000. 30 times 12, 10 minus 7.6 inches squared is 3456. Add them all together, I get 30,773 inches to the 4th about the minor axis. Okay, so that gives me Ix and Iy. Now what I want to do is find the products of inertia, and I have 2. I have A1 and I have A2. So A1, I got 8 times 50 times 8.5 minus 7.6 is dx, and 30 plus 50 over 2 minus 31 is dy. And that equals minus 34,560. Products of inertia can be negative. Moments of inertia cannot be negative, but products of inertia can be. Terms are not squared, so a section to the left of the center of gravity is going to be negative. A1 is to the left of where the center of gravity is, so it's negative. For the Ix2, again, the same typo, 12 times 30, and then I have the x direction is 8 plus 12 over 2 minus 7.6. The y direction is 30 over 2 minus 31. Gives me minus 23,040 inches to the 4th. Same note. And so my product of inertia, Ixy, is the sum of the 2, minus 57,600. Okay, so now I have all the pieces. I can calculate Imax. Imax is Ix, Iy, plus Ix plus Iy over 2 squared, plus the product of inertia squared. And I max is 519, 127. I min, same thing, only this time you're subtracting the square root of the sum of the squares. And that gives me 23,979. So you notice that the maximum is greater than Ix, the minimum is less than Iy. And then if we solve, actually, let me get rid of these now. Okay, then I'm going to solve for the axis orientation. So it's half inverse tangent, 2 times minus 57,600 over 30,773 minus 512,333. And that comes out to be 6.73 degrees. So as a summation, I max is 519, I min is 23,979, theta is 6.73 degrees. Those are my boxed answers. And so here's the section we started with the coordinate axes, X and Y. Here is drawn to scale the actual principal axes. This is what's known as the principal axes, and they're rotated by 6.73 degrees. So about this X prime axis is the maximum moment of inertia you can attain with this section. And about this Y prime, so what's really interesting is when you rotate the axes, you rotate them both together. They're still 90 degrees apart, but the maximum is always 90 degrees away from the minimum. So if I found the maximum is at 6.73 degrees rotated, then the minimum is also rotated 6.73 degrees, and it's about this slanted axis here. Okay. Any
Excuse me,
questions?
Professor.
Yes.
So this theta, when you rotate it about the x axis or the y axis, or for both, you get same theta.
Same theta, yeah. Yeah, you're basically taking the whole system and rotating it. Okay, any other questions about these problems? I can tell you in, I don't know, sometimes students appreciate when there's some real world practical, why are we talking about this sort of thing? So here's a real world situation. We have in the world of steel, again, I'm a concrete guy, but I have to ramble into the world of steel from now and again. And we have in the world of steel these things that are called angle irons. So that was weird. Okay, never mind. Can I grab that? I can't do anything with it. All right, well, anyway, it's a piece of iron that is shaped like this. There's only a little gap there because it's the way I could draw it. But when you have a hot rolled piece of steel in the shape of an L like this, it is highly unsymmetric, very highly unsymmetric. And so if you use this sort of section as a beam, use it like a lintel beam, if you assume that this is going to be bending about a x-axis, like this is really getting wonky. If I have an x-axis and a y-axis, and you assume that this is going to be bending like a beam about the x-axis, then you would have a moment of inertia that you would calculate about the x-axis. And then you would take your load, and as we're going to do in a few weeks, you figure out how to find stress due to bending. The flexural equation that we're going to be presenting in a little bit is my over I. And so what matters is what y do you use and which I do you use. And my point of all this is that this particular angle, the principal axis, is actually here and here, like so. You guys can still see my screen, right?
Yeah.
Okay, okay, good. So if it's bending about this orange axis instead of the red axis, their stresses are going to be much higher than if you had assumed it's bending about the x-axis. So if you don't know about principal axes, if you've never been made aware of principal axes and how they work, you could grossly underestimate the stress in this steel beam by using the wrong moments of inertia. Okay, that's my ending point. Any questions? Alrighty. So that concludes this presentation, and I will definitely go back and fix those typos. All right, so we can kill this.